Hello again, welcome to this video. So here we will see how to find HT and then we will see how to find the distribution DT. So till now we have seen how to use the exponential loss, why it can be used. We have also seen how to find the weights corresponding to each of the HT, which is basically the alpha T. And now we will see how to find HT and DT. Okay, so how to find HT? We have the ensemble of all the classifiers from small h1 till small ht minus 1, and they have ensembled to form capital HT minus 1. Now how to find HT? So if we add HT with the current ensemble, it will minimize the loss. So how to find the loss? As we have seen, it is expectation. So e power minus fx into hx. So what is hx here? HT minus 1 plus HT. Now, if we use the Taylor expansion of e power minus fx htx till 2 degrees, then the exponential loss can be approximated as this. This is simple Taylor expansion. Now, why we have not used the second degree terms? This is because this fx square equal to 1 and htx square equal to 1. So we have not mentioned them in the third term. Okay. Now for simplicity, we have just written the value 1. Okay. Now how to find this ideal classifier HT? This can be found by minimizing the loss over all the h, and the terms, the argument in the loss is ht minus 1 plus h. So we have to go over all the hypotheses, add it to ht minus 1, whichever is the minimum, that will be our ht of x. Okay. Now, so what is this loss? We have seen this equation earlier in the previous slide. Okay. Now, if we see that 1 plus half is 3 by 2 minus this fx hx, if we take out the minus to outside, then this argmin should become argmax of h. Okay, now this is argmax of h, and inside is e power minus fx, capital HT minus 1 of x. This is the combination of all previous ensembles into fx into hx. Okay, that's fine. Now we are dividing it by some huge horrific terrific term. So what is this basically? This is a simple normalizing constant to convert this thing into a probability distribution. Okay, now we have seen earlier is term zt in the algorithm. So in the Adaboost algorithm, so this zt is basically acting kind of this. Okay, so this is about how to find HT. Now we will see how we can simplify this. Over to Sohan.
Okay, so we saw a huge expression for HT. Now in this slide we will see how to get a compact expression for HT. Now for that, let us denote a distribution dt as d of x into e to the power minus fx ht minus 1x divided by expectation of e to the power minus fx ht minus x. Now in the previous slide we saw the expression of htx as the first line. You can see that argmax of expectation of that huge term. Now e to the power minus fx into ht minus 1x, this term is already determined, right? So as you can see how this term is already determined, like we know the ensembling hypothesis for all the base learning algorithms till t minus 1, and similarly the expectation value in the denominator is also a constant, and we already know it, like it is just the exponential loss till t minus 1 term. So what we do is that we just we can just ignore it, as we are just finding the maximum value of the term. So we just take argmax of fx into hx. Like the logic behind ignoring this term is that they are just constants, and the distribution just changes from d to dt, as we have now sampled x from the new distribution, that is dt. Now notice that fx into ht of x can be written as 1 minus 2 into indicator function fx not equal to ht of x. This is quite straightforward. Now using this notion and putting the value of fx into ht of x in the above expression, we obtain, like you observe one negative sign introduced, so argmax becomes argmin and rest of the terms remain same. Like we take the expectation over the indicator function of fx not equal to hx, right? So this is the compact form of ht. Now we will use this and look at how we can derive a relationship between the present distribution that we have and the distribution that we are going to sample for the next hypothesis ht plus 1. Okay, so previously you saw that I had defined dt of x is equal to dx into e to the power minus fx h t minus 1x, right? So in the argument of exponential function, we had ht minus 1x. So but just replacing t by t plus 1, we obtain this expression like, so dt plus 1x will be equal to tx into e to the power minus fx capital htx divided by the expectation term. Now you observe that ht of x can be written as ht minus 1 plus alpha t htx, right? This is the method we are using for ensembling the weak learning algorithms, weak learning models. So the exponential function can be splitted into two multiplication terms, that is e to the power minus fx into ht minus 1x into e to the power minus fx alpha t htx. Now now let us divide expectation of e to the power minus fx into ht minus x in the denominator and multiply the same. So in the previous slide, we saw the definition for dt of x. This simply boils down to that expression like dx into e to the power minus fx ht minus 1x divided by that expectation simply boils down to dt of x. And since we had divided it, we need to multiply it. So you can see that the ticked term, the cross check term, is that term which we are going to divide and multiply, and the rest of the things remain same, that is e to the power minus fx alpha t into ht of x. So what we have here, we have the distribution for t hypothesis, we have the exponential loss function for t minus 1 hypothesis and t hypothesis. We also know the weight as we have already derived it. So we get a distribution that we need to sample for the next hypothesis ht plus 1, right? So we get dt plus 1. Well, this completes the derivation of relation between dt and dt plus 1. In the next video, we are going to look at the gradient boosting part, which will be the last for this series. Thank you.